Digital circuits. Okay, silicone diode, 0.7 volts is where it turns on. Germanium diode, 0.3 volts where it turns on. In practice, I can buy a diode designed to turn on any place I want it to. It's just the amount of how much money do I want to spend. Okay, so I can have one at 0.7, it's going to cost me 15 cents a piece. I can have one at 0.72 and it'll cost me $100 a piece. And it's the same diode. All I did is have somebody go and test it and find the ones that were 0.72s. And I'm just going to charge you more for it because I'm that type of guy. Okay, so we'll look at the guy on the bottom. And so I've got 5 volts. I've got a resistor. Oh my God, it's 1K, 1 kilo ohm. I got 0 volts on this side. I've got a diode going that way. I got some voltage over here, voltage 6. Is it voltage 6? Yeah, voltage 6. And then I've got 5 volts on this side, like that, coming up to there. Okay. So I'm going to have some voltage drop across that, across this guy, right? I'm going to have a 0.7. First of all, this guy's forward biased. Forward biased. So I'm going to have a 0.7 voltage drop across that resistor. My voltage at 6 is going to be 4.3 volts. 5 minus, no, is going to be 0.7 volts. So I'm 0 on this side of the diode. I have a 0.7 volt drop across the diode. Voltage at 6 is going to be 0.7 volts. I look at this diode and I see I'm positive on that side and I'm at 0.7 on this side, which means I'm negative. This guy's reverse biased. So nothing's happened with him. I look at how much current is flowing and I see I got 5 minus 0.7 divided by 1K, which is the awesome 4.3 milliamps again. So I figured out which diode's forward biased, which diode's reverse biased. The ones that are forward biased has a 0.7 voltage drop. I have current flowing through it. That means current has to go through some resistor. There has to be some voltage across that resistor. And that's the way I look at those things. Okay.
What I don't get on that schematic is where like the V6 is.
Yeah.
Your voltage is 6 on that last page.
Mm-hmm.
Is that saying that's like the current is it 6 or where is that pointing to?
The voltage is at 7.7 volts. It's V6 because it's the 6th example. So
Okay.
this is a 6 because there was a V1 and a V2 and a V3 and a V4, a V5 and a V6.
Okay.
So it's a lowercase. It's a lowercase 6. It's the 6th problem in the problem set. That's why it's a V6.
Okay.
Okay.
So it's not part of the schematic at all. Okay, got it.
Right. So 0.7 is the voltage that's at V6.
All right, so what you've got then is it starts at 5, it goes through that resistor, it hits that diode, it's coming out on the left at 0 volt with the problem solved over
That's
there.
right. So it's 0 volts here. 0.7 drop means it had to be 0.7 on this side. Exactly. And then the other guy's reverse biased. It's not part of the problem at all. Because this side's positive compared to this side, which is negative. Even though this is a positive voltage, this is positive 0.7 volts, but in comparison to the plus 5 volts, this side is positive, that side is negative. The diode is reverse biased. Okay, next we'll talk about a transistor. And this happened just before World War II, just so that we could have a better way to kill off our fellow man in World War II. And so what we did, a diode will have a negative and a positive junction associated with it. So that's a diode. The transistor will have three layers of material, a positive one, a negative one, and a negative. Negative, positive, negative. So I could have a N, P, N transistor, or I can have a P, N, P transistor. Positive, negative, positive. I could have both of those. The symbol for the NPN transistor looks like this, and the PNP transistor looks like that. I have now when we came up with transistors, we still had tube-based technology that was 50 years before. So the words we're using to describe this terminal, we call it the collector. And we call this guy the base. And we call this guy the emitter. But we call them that because that's what they were in our tube technology. So we took our vacuum tube technology. We now have this NPN transistor that's doing the same thing that the vacuum tube used to be doing, and we brought with us the same words associated with the vacuum tube. Now, the vacuum tube is something that is going to be electron flow, because we can't describe how a vacuum tube can possibly work if we have positive holes flowing. IEEE decided that when we went to transistors and diodes, and from then on, we would discuss the issue as a positive current flow. So my positive current is going in one direction. In the opposite direction are my electrons that I don't care about anymore, because I'm only talking about the positive holes flowing down the wire. Okay, so that's a stretch,
Yeah.
right? But that's how we're going to think about it. So current is positive. We have positive holes flowing down the wire that way. Unless you're in the Navy. If you're in the Navy, then you have electrons that are flowing the other way. All right, so when we think about this NPN transistor, we've got a thingy here that looks sort of like a diode. We have a collector, a base, and an emitter. And if there's going to be current flow, it's going to be that way. Now, why would the current flow from the collector to the emitter?
If you collected it, now it's got to transmit it.
So it wouldn't. But if this were a vacuum tube and we had electron flow, the electrons are leaving the emitter and going to the collector. That would make sense. But we brought those words with us, and so those are the words we're stuck with. The transistor, because this is a digital circuit class, the transistor is on. When it's on, we say it's in saturation. And that means there's current flowing. Or the transistor is off, and we call that cutoff. And we really don't care about anything in between. Okay, we don't care about anything in between. It's either in saturation or cutoff, because this is a digital circuit class. We want it to be on, we want it to be off. We want to use the transistor to be a memory location. 1 for on, 0 for off, keeping track of my memory. So we don't think of the other uses of the transistor, which we do next semester. Now the transistor has a characteristic curve. And it looks like this. Oh, this is so terrible. Give me some space here so I can draw a characteristic curve. Okay, so this is voltage. This is current. Oh, that was good. So these are voltages at the base. So this would be like 1 milliamp and 2 milliamps, 3 milliamps at the base, going through the base, 4 milliamps, 5 milliamps. And as my voltages change, I would go that way. Now, next semester, we'll see that there's a load line that goes through here. This is cut off. And this is saturation. And my AC signal is now fluctuating up and down on either side of the load line as my whatever happens on the base does. And now I can get amplification out of that transistor. This is a digital circuit class. We don't care about amplification. The transistor is either on or the transistor is off. The transistor has voltage at the base, in which case it's on, or it doesn't have voltage at the base, in which case it is off. Okay, so I'm going to look at the guy on page 46. And I'm going to have zero, I'm going to ground over here. This is 0 volts. So I got a ground. I got some resistor, base resistor going on. And I got some collector resistor going on. I've got plus 5 volts. And I'm grounding on this side. Because there's no voltage at the base, I'm at 0 volts, this guy is off. So if I go and have voltage out be right there, what is the voltage out going to be? If I have 5 volts here and the resistor is off, there's no current flowing through it, that means I have to have 5 volts coming out. Okay? I go and I do something silly, and I go and I say I'm going to put 1 volt there. So now I got 1 volt at the base. The transistor is on. When the transistor is on, I'm now connected to ground. My voltage out is going to be 0 volts. No, it's not. It's going to be 0.7 because there's a transistor there, but because this is a digital circuit class, we're just going to call it 0. Okay, so we're calling it 0 volts because it's convenient for us to do so. We're using the idea of an ideal transistor. It's going to be on, it's going to be off. We really don't care about any of the in-between stuff. We'll worry about the in-between stuff later. So now I've got a thing that I've got an input signal that goes, well, I'll call it voltage at the base. Our voltage at the base is low, it's high, it's low, it's high, it's low, it's high, it's low, it's high, it's blah, blah, going up and down. 0 volts, 1 volt. And my output is V out. When I'm at 0 volts, I'm going to be high. When I'm at 1 volt, I'm going to be low. And I'm going to be, look a signal sort of like, my output's going to look sort of like that. And I'm going to have 5 volts when I'm high, and I'm going to have 0 volts when I'm low. And now we have to do something. We have to call this circuit something. So what would you call a circuit that when I'm high, it's going to be low, and when I'm low, it's going to be high?
Inverse.
alternating,
current.
alternating, reverse. No, we don't use either of those words. Those are words we have already used for something else. You need a new word, right? We have reverse. We use that reverse bias. We already use that word. Alternating current, alternating thing, AC. We're already using alternating, so we need a new word. Anybody got a new word?
Inverse.
Right. So this is going to be called an inverter. Inverter. And it's going to have a truth table. So this is input A, and that's the output. So, and my inverter is going to look like this. So that's what the symbol for my inverter is. And when A is 0, the output is 1. And when A is 1, the output is 0. Okay, and I can make that with a diode. I'm not going to make it with a diode. I'm going to make it more complicated than that. But I could make it with a diode, a transistor, right, whatever. So we do it again, and on page 49, we call this transistor to transistor logic. And we have the inverter circuit sitting there. Isn't that wonderful? And we go and we calculate what the output is. We go and turn to page 50 and 51. We see we have the inverter circuit made more complicated so that it works better. And now this inverter which has a symbol that looks like that, AX, is now, I'm not going to use it, I'm not going to build it out of transistors and diodes, everything I want to use it. I'm going to go and put it on a chip, a dual inline chip, dual inline DIP, yeah, package, dual inline package. And what I'm going to do is I'm going to have pin 1, pin 2, pin 3, 4, 5, way to go, 6, 7. Okay, so I'm going to have those pins. And then on the other side, thank you very much, Eraser. That was very kind of you. I didn't want that stuff to stay there anyway. And then on the other side, I'm going to have pin 14, 13, 12, 11, 10, 9, 8. And then I'm going to go and I'm going to ground pin 7. So pin 7 is going to be the ground. I'm going to hook up 5 volts to pin 14. And then I'm going to have 6 different inverters sitting on here that I can go and use. Way to go. Just, that looks so much like an inverter, I tell you. And these other guys go the other way, right? Yeah. Now take your book and open it to the front cover. And you see that in the front cover you have the 7404 inverter chip looking exactly like I drew it on the board. 7404. So the 7404 is the inverter chip, TTL logic, plus 5 volts on the input, and we're going to use that for lots and lots of things. Okay? So
74245.
Which one?
74245.
Yeah, probably. You know, we can tell. But it's something you're gonna use so often, and if you need it, it's there in the front cover of your book. Okay, the inverter. Multi-sim simulations. Okay, we don't care about that. As things got better, so this is TTL logic. The problem was this takes 5 volts. With 5 volts, that's not very much, right? That's not going to cause too much current. But as we put more and more of these on a chip, we end up getting hotter and hotter, and it became a problem, and we had to do it differently. And so the technology was fine as long as we had 1,000 guys on the chip, but we went to 100,000 things on the same chip. We now had problems with heating. So we go to Cmos technology, and the Cmos technology allows us to use MOSFETs, which are field effect transistors. Instead of using the PNP guys, they turn on differently. You'll find that out next semester how they turn on. I'm not going to bother to tell you. And now we put them on things, turn the page over to 54, we find that we can now do it with surface mounted techniques, and we don't have to put pins all the way through the printed circuit board, and we can make life so much easier for us in doing things like that. So I found that in the fabrication process, and I've got some board with 1,000 chips on it, I'm going to go and put my my solder on as a paste. I'm gonna mask it on, and then I'm gonna place my surface mounted technology guys in the right spot using a robotic arm thingy, through 2 or 3 of them to put them on, and then I'm gonna send it through an infrared oven, and all that solder is gonna melt uniformly, and every single point's gonna be really great. And I fired all the little old ladies in tennis shoes that used to do my soldering. So in the 50s, when I made a television, I'd have a bank of 100 little old ladies in tennis shoes soldering these wires one at a time in an assembly line. Now I don't do that anymore. Now I go and make that television board. I put all my components on, I send it through a microwave oven, and now I have a little old lady sitting there soldering a power line on. And so she has 3 wires to hook up, the power, the common, and the ground. And the other 99 little old ladies all retired and are living happily ever after in Florida. But I needed the Cmos technology to get and that's complementary MOS, which means nothing to you right now anyway, but that doesn't matter. We're just adding vocabulary words to your vocabulary. We needed it to get the power, the amount of power used to turn the transistor on and off to a lower level, so we use less current. Less current means less heat, because in circuit analysis you have power is I squared R. So the more current, the more power. That power is going to be dissipated as heat. V squared over R, V times I. Okay, any questions?
Is that in the book, the formula,
Which one?
the one you just wrote?
It's in your circuit analysis book.
That's what our,
Yeah. So you in circuit analysis, you've done V is equal to IR, right? You've done that already, Ohm's law? You may not have. It might be chapter 3. You may not be there yet. And then you have power is voltage times current. And then you can substitute this back into that equation. So power, if I substitute the V as IR, I can have I squared R. If I rewrite this and say current is voltage divided by resistance and put the current in there, now I've got V squared over R. So now I've got power, 3 different equations for power. Okay, back to doing homework problems. And we're starting with number 6. Number 6. Determine if the diodes in figure down below P26 are forward or reversed. P
What page is this on?
to 58. 58
58
and 59. All right, so I've got
well, which one are we on? Where?
58 is the problem
Okay.
on page 58, but the figure we're looking at is on 59.
Okay, so 58.
Yeah. So we want to know D1, D2, D3, D4, D5. How many do we have? D6, D7, up to D13. D8, D9, D10, D11, D12, D13. Okay, so those are the answers we're looking for. And we're looking for forward, reverse. That's all we're looking for. Okay, so I look at the A drawing, and I say I've got plus 5 volts, and I go through a diode over here, and I go through a diode over here. All right, that's good. And I come down here, and I've got 5K. And I come down here, and I've got 10K. And I'm grounded. All right, so that's what I got. This is plus, this is minus, that's plus, this is minus. So D1, which is that guy, is reverse bias.
Where is this figure?
On page 59.
On the top of page 59 with the little in parentheses A on the top left.
I see.
Okay, I'm missing, I didn't draw in the V1 and the V2 because I really don't care what V1 or V2 is until I get to the next problem, which is asking me what V1 and V2 is, and I have to redraw the whole thing over again. And D2, I'm positive, I'm negative, I'm going to be forward biased. All right, so now I'm looking at the B picture. B picture, I've got plus 5 volts. I got a diode, calling it D3. D3. I've got a ground. I have a diode, calling it D4. I'm hooking together, and I'm coming down to a 10K resistor, and I look at D3, and I see on this side I'm positive, on that side I'm negative in relationship to that. So D3 is going to be forward biased. Okay, that being the case, I'm going to have 0.7 volts there. If I'm 0.7 volts on this side, I'm positive on this side, I'm negative on that side. D4 is reversed biased. Okay, I'm going to look at the C problem. I got 5 volts. I got 2 resistors, 10K and 10K. And I come out this way, and I've got a diode going to ground. I see that I'm negative on this side, I'm positive on that side, so I'm going to be, what is this guy? D5. D5 is going to be forward biased. Okay, now we're looking at the D guy. I've got 5 volts. Got a D6. And I got a D7. And come down this way. Got some voltage out that way. I got a resistor down here, and I'm grounded 10K ohms. I see that I'm positive on that side, I'm negative on that side, so D7 is forward biased. I see that I'm positive on that side, negative on that side. I see that D6 is reverse bias. And moving down to number for E, and I've got 5 volts, 5 volts, 5 volts, and 3 diodes that are reverse biased. Uh-oh, maybe not. 5 volts, and I have something coming out this way. V6. All right, well, I have 5 volts on this side, and I have 5 volts on that side. So I'm neither forward nor reverse biased. Neither. By spelling the I before E except after C, right?
Wouldn't you be reverse biased since you got voltage drop across that resistor?
But
That's what I was saying.
there's no current flowing through the resistor, so there's no voltage drop across it, so therefore I've got 5 volts on both sides.
So how do you determine where the current comes from?
Say again?
How do you determine where the current comes from when you're driving it?
Well, current has to go from something positive to something less than that number, whatever it is. But there's no flow of current. I need,
Because it's all 5 volts.
yeah. So current has to be flowing in order to have current. So because there's no current flowing, I have 5 volts on this side of the resistor, 5 volts on the other side of the resistor. I have 5 volts on both sides of my diode. So the ideal diode is neither forward nor reverse biased in this case.
Or would you actually have no volts on either side since nothing's flowing, since there's nothing to attract?
No?
Mr. Cordova, neither is spelled wrong.
I misspelled neither already.
It's N-E-I-T.
I had it right the first time? Oh. So, right, in order to have a voltage drop, I have to have current flowing.
There's no
In order to have current flowing, I have to have a path for it to flow. There's no path.
You see that after
I have 5 volts here, I have 5 volts there, I got 5 volts here, there's no current flowing. Now, if I were to go and put a resistor over here, that would be different. Now I have current flowing, now these guys are all reverse biased. Okay, but as the picture as drawn has no path for current to flow. So neither. So that's a weird one, I agree. There's nothing weird about that. And how about the next one? How about the F guy?
See, there's no power.
That's right. So there's no voltage on the diode on either side of the diode. So it's neither forward nor reverse biased. So it's neither too.
That's all.
Neither. And that example is more easier to see because you can't be confused about current flowing when there's no voltage, right? The other one you could technically be confused. Now 2.7, we want to do the same thing over again, and this time we want to find 2-7, and we're looking for voltage 1, voltage 2.
I think we go to 10. Yeah, we go to 310, not 2.7.
Oh, we don't do 2.7? I'm looking in the wrong spot. Okay, 210. Good, excellent. Two dash 10. Find voltage out 1 and voltage out 2 for the circuit P210. Okay, so I've got 5 volts going to my base. I got 1000 K, and I got a ground hooked up to my emitter. I have 10 K, and I've got 5 volts up here. And where is V out? There's V out. V out 1. Okay, and then we'll draw the other circuit. I got 5 volts going to 100 K at my base. I got a resistor at the emitter of 10 K. I'm grounded, and I've got V out 2. And I've got 5 volts up there. All right, so I look at the first circuit, and I say, well, I have 5 volts on the base. This guy is on. Okay, so if he's on, my voltage 1 is going to be 0 because I'm grounded. This is a digital circuit class. It's either on or it's off. Circuit analysis class, devices class next semester, we're going to say it's 0.7 volts because there's a 0.7 volt drop across that diode. We are unconcerned about that because we are digital people and we only think ones and zeros. We're not allowed to think anything other than that. Okay. When it's time to think something other than that, I'll tell you when that is, but now is not the time. All right. I look at this guy. He's on. Okay, so current is flowing, and I'm dropping 5 volts across that resistor. My V out 2 is going to be 5 volts. It's 5 volts because this is a digital circuit class. We're either 0 or 5. Next semester in circuit analysis, it'll be 4.3 volts because there's a 0.7 volt drop across the transistor sitting there. We don't care about that. We didn't care about that in the A part of the problem. We're not going to care about it in the B part of the problem. Okay.
Why is that one 5 and the other one 0?
Because this guy's on, my V out is connected directly to my ground. It's at 0 volts. Here, I'm on. I'm still on, right? But now I'm on. My voltage is going to be at 5 volts there, and I'm going to drop the 5 volts across the 10 ohm resistor. So when I put my output at the collector, on becomes a 0, I become an inverter. When I put my output at the emitter and throw in an emitter resistor, my on becomes an on, and I become a buffer. So an inverter symbol looks like this. That 0 means I've knotted it. A buffer symbol looks like that. It's not knotted. Okay, so I've gone and whatever I have on this side, I get on the other side. I'm a buffer. When this guy goes off, that guy goes to 0. When this guy goes off, this guy goes to 1. He's an inverter.
So on the left, where's the ground? On the left.
Right here.
It's at the bottom.
Yep.
But the out's on the top, so how does that go to the ground?
Yep. Well, my voltage, this guy's on. So that being the case, I have current flowing. I have voltage drop across the resistor. And now I'm connected directly from there to ground because the transistor's on. And that's the case because This is a digital circuit class.
So that's why it's zero, so isn't the an on the other side of the transistor?
Yeah, when the V out's on the other side of the transistor, I'm still on, but now the voltage drop happens after my V out. See, in this thing, I do my voltage drop first, and then I get the V out. In here, I get my voltage first, and then I do my drop across the resistor. Yes, yeah, depending on whether or not it's hooked at the collector or the emitter. Yes.
So the voltage was 10, because the resistor was still zero. The voltage was 10, and the resistor was still zero.
Right. So the question is, if I had 100 volts up here, what would be the voltage out 1? 0. If I had 100 volts out here, what would be the voltage out 2? 100 volts. Except for one minor insignificant detail. Anybody know what it is?
What was that?
At 100 volts, I probably burned up the transistor. Yeah. So 100 volts, probably sending too much current. I just burned the damn thing up. But other than that minor insignificant detail, this is a digital circuit class. It's on or it's off. We could say I got 1,000,000 volts there. We'd be perfectly happy saying it's 0, it's 1,000,000 volts. Okay? But in reality, I just burned up my transistor, which is something that I wouldn't want to do. Unless I really wanted to do it. So that's 12. What was that? That was 10. All right. So after 10 comes 12. 2-12. To use a common emitter transistor circuit as an inverter. So the issue is, what is a common emitter circuit? And clearly it's in the book, but that's beside the point. So what does common mean? If I was going to come up with another word for common.
Neutral.
Neutral, right. So common means, where is the ground? Where is the ground? So if the ground is here, I'm common emitter. If I make a circuit and I do this, then this is common base. My common's at the base. And if I make it, I could have a common emitter, I could have a common collector if I had a circuit where that guy's grounded. Now I'm common collector. So it depends. It's telling me where my ground is in the circuit. And in the 2 months of transistor theory you have next semester, you'll find out that each of those circuits have a different capability as to how much current they can pass, what their gain is, what their voltage gain is, what their power gain is. But again, in digital circuits, all we care is on and off. Okay, so common emitter has to be a circuit where the ground is on the emitter. Okay, so the question is, in a common emitter circuit, so I got this, boom, 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 and I got that, blah, 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 and I got some voltage CC on the collector, and the common inverter, so I want this to be an inverter. Okay. The input signal is connected to the base. So base goes in the first hole. And the output signal is taken from the collector. And we saw this circuit before. We had it on as an example before we got to the homework. When this guy is 0, he is off, that guy is 1. When this guy is 1, he's on, and the output is 0. Now we have a collector. A 0 gives us a 1, a 1 gives us a 0. Logically, 0 volts gives us 5 volts, 1 volt gives us no volts.
So are you saying that when the base is off, it goes to the collector, when it's on, it goes to the emitter?
No, when the base is at 0, or smaller than that, it could be at minus 500,000. It wouldn't matter.
But we do it on and off in this
Yeah.
class, right?
So yeah,
Okay.
so the transistor is off. When the transistor is off, whatever the voltage here is, has to go through, the current goes through that resistor and comes out there. There's no current flowing, so I would have 5 volts on my output. When I have a 1 there, I'm turning on, 1 at the base, I'm turning on the transistor is on, now the current flows that way, and my ground is hooked up to my voltage out, and I get a 0. Yeah. So when the transistor's on, I end up getting a logic 0, no voltage. All right, next guy. 15. In the circuit 235. All right, so now I got to go find 235. 235. Okay, so I found 235, and 49, I think. So we got a resistor of the base, and the emitter is grounded, and we have a resistor at the collector, and we have plus 5 volts, and we have a voltage out, and we have some resistor load. Okay, so I got a 4.0 for drawing the picture. Okay, moving back. Let's see. In the circuit 235, when Vn, oh here's Vn, when Vn is equal to 0 volts, V out will be almost 5 volts as long as V load is much bigger than Vc. Okay, have you asking a question yet? Why not make Vc very small to ensure that the current will work for all values of our load? Okay, so the issue is if our load is much bigger than RC, then V out is equal to 5 volts, about 5 volts. All right, but it wants us to make, what happens if we make VC really low? So what if we took this guy out altogether? Yeah. So if I go and I remove this guy altogether, I put a short about him, why wouldn't that be okay? Because now I would get the 5 volts I want, and it wouldn't matter what the load is. The load could be 1K, the load could be 2K, the load could be 100 meg, the load could be 0.1 ohm, and everything would work wonderfully, right? So why don't I just do that? Yeah, so the problem would be, what happens when Vn is 1 volt and this thing is now on, and now this resistor is very small? What's going to happen? So this resistor, among other things, is a current limiting resistor. A current limiting resistor preventing the transistor from burning up. If I make it too small, too much current will go through the transistor when it's on. My transistor now burn up, and what did that do?
Heats it up.
No problem, right? Guaranteed employment for the electronic technician. They should design it that way. You guys would have a job the rest of your life replacing transistors. And all you do is sit around, every day, replace the same transistors you replaced yesterday. No problem, right? Yeah. The engineer would find that a really bad idea, right? But as a technician, why would you think that was bad? I mean, you're getting paid, your Social Security is being paid into, everything's wonderful. Yeah. So that's the reason. The reason is that RC, part of the reason there is a resistor at the collector is to limit the current through the resistor, through the transistor, when the transistor is on. That's part of the reason. There are other reasons for it to be there too, but that's the primary reason. 2-19. 2-19. Y1 in the 4096/4197 control card schematic sheet number 1 is a crystal used to generate a very specific frequency. A, what is its rated frequency? B, what time period does it create? Okay, is there anybody that doesn't recognize any of those English words? Okay, all those English words are all recognizable as English. Okay, now, in the sentence that they're in, is there anything in there recognizable at all? No, I mean, talk about a question, what the heck, Okay, so in the back of your book, maybe, unless you haven't used one, you have a schematic sheet. And that's why it has an S there. See that S there on problem 2-19? It's S for schematic. All right, so I got the schematic sheet out. Okay, because I know I'm supposed to look at it. Okay, so I'm looking at it. Now I'm trying to find the 4096/4997 circuit. Okay, so that's the one in the top left-hand corner. There's 4 of them, but the top left-hand one in fine print on the bottom right of that guy says 4096/4197. Yeah, the fine print. See the fine print? See the title box. The title box, lower right title box of the upper left section. Right, bottom right of the upper left. Okay. All right, so now we got the right schematic. Now we have to find Y1. Y1. Okay, I see Y1. Y1 is in C1. So you see in C1 there, you see the Y1 guy? So I see Y1, and it's a symbol that looks like this. And next to it in fine print, which I can barely read, it says 8.0 megahertz. 8.0 megahertz. Okay, so it's an S problem. I need the schematic. I need to find which schematic I'm using. I have to find the component on the damn schematic, and then I need a magnifying glass to read what the stupid thing says. Okay, so you got all that? All right, now we can solve. Now maybe we can solve the problem. So put your schematic back and don't lose it. Now, if you lose your schematic, just come to me sometime and we'll Xerox one off for you. All right, so what does the problem say? A, what is the rated frequency? A,
I don't have a schematic.
8.0 megahertz. That's right, you got it used. Okay, so that's fine. Follow me after class and we'll make a copy of the schematic for you. And it won't be a problem. Okay, so it's 8 megahertz because the schematic said it was 8 megahertz. All right. What is the period? Well, the period is 1 over the frequency. So I want 1 over 8 megahertz. And we can do that in our head, right? 125 nanoseconds. Is that what it is? 1 divided by 8 double E 6. Yep, that's what it is. And then we'd ask ourselves, self, how many significant digits do I have? 2, 8.0, right? So I have 2. So I would round that off to 130 nanoseconds, and I'd call that my right answer. If you kept it that way, that'd be perfectly okay. I'm not going to complain about one lousy significant digit, right? Yeah, I did. Didn't I write 130? It's on the front row there anyway. Now I got it. Now it's all hosed. Yeah, you do. You're about to complain about that, right? Nanoseconds. All right. But either the 125 nanoseconds, 130 nanoseconds, I would mark both of those as correct. Okay, now we got 1, 2, 3 more problems to do. All right, so we're going to go and start multisim. Where's my multisim program? There it is. And because I've already downloaded all the files already on Tuesday, they're still on my laptop, right? On my desktop, where I can easily find them, right? I don't know. We'll find out, won't we? Either that or we're going to spend the next half hour finding them on the web again. Those are my two choices. All right, so I got multisim open. During our lab periods next week in circuit analysis, we'll go over to the lab and I'll show you where the multisim programs are so you can use them on your own. Let's see, we're supposed to open circuit 2-3. All right, so file, open, my computer, the C drive. Where's the desktop? Desktop, there it is, I found it. There's the TestGen program? No. Factory Talk? No. Oh, I'm so hosed. Why isn't that there? Okay, so we'll come out of here. There it is. There they are in plain sight. So we got them open. We're going to go to Problems, version 9, chapter 2. Okay, we're all set now. Section 2, 3. Haha, there we go. Well, we don't care about the description, right? Okay. Determine the 3 ASCII characters that are transmitted in serial. The 3 ASCII characters transmitted in serial. Okay, you ready? Oh, it says read the we forgot to read the instructions. All right, we'll turn it on. Okay, there we go. So we have 3 ASCII characters transmitted in serial. All right, thank you very much. So I'm looking at this, and I'm saying, can I make it bigger? Bigger. Bigger. How come this isn't getting bigger? Oh, that's much better. Is that much better? Okay, so that's much better. Okay, and I can go and do something like this. I can't. Oh, I can. Whew, there we go. So I got it there. Okay, so I look at it and I've got. We'll look at the leading edge. So at the leading edge of the clock pulse, I've got a 0, I've got a 0, I've got a 1, I got a 1, I got a 1, 1, 1, 1. Then I've got a 0, then I got a 1. This isn't going to work. I lost my place already. Yeah, you got a bright idea?
I wasn't here Tuesday, so I missed whatever you did Tuesday to explain this, so.
Excellent. Well, we didn't do anything to explain this on Tuesday, so don't worry about it.
The clock?
Yeah.
I'm confused.
So this is the clock, and we're transmitting a signal down here. So we're going to have to figure out what the damn signal is that's being transmitted, and we know the most significant bit is going to be this one on this side, right? So we know that. So we're going to go with a 1, a 1.
Where are you getting these numbers from?
Right there. See that 1? Your signal's 0.
I don't see any numbers.
Well, right here, your thing. It's either high or it's low. So here it's low, there it's high. There it's low, there it's high.
Low is 0
There
and
it's
1.
Yeah, exactly. So back to what we're doing. We're gonna look at the leading edge. I got a 1. The leading edge, I got a 1. The leading edge, I got a 1. The leading edge, I got a 0. The leading edge, I got a 1. Okay, I'm here. Okay, the leading edge, I got a 0. I did that one. On leading edge, I got a 0. Leading edge, I got a 0. Leading edge, I got a 1. No, those are dits, meaning I've already done it. Those are not ones. Those are dits, meaning that's where I am, so I know where I'm going back to. All right, so I'm doing this one, that's a 1. I'm doing that one, that's a 0. So you want me to do something like an X like that? That's a 0. I'm doing an X there, that's a 1. I'm doing an X here, that's a 0. I'm doing an X here, that's a 1. I'm doing an X there, that's a 0. I'm doing an X there, that's a 1. Doing an X there, that's a 1. I'm doing one here, that's a 0. Doing one there, that's a 1. Doing one there, that's a 1. Doing one here and here, 0, 0. Okay, so now I got the guy, right? But I know that this is most significant bit on this side, and this is least significant bit on that side. Okay, so I'm going to have to turn it around before I do anything with it, and I'm going to divide it up into 7. 1, 2, 3, 4, 5, 6, 7. Because ASCII is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, you stupid thing. Okay, so obviously it's transmitting ASCII in 8 thingies. I can't get rid of that other thing, so I'm going to go and...
Yeah, wouldn't you go start on 7 on the right?
And then most of them have it.
1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 1, 2, not the green guy, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. How come I don't have an 8?
Yeah, you counted too many.
Which one did I count too many on?
First one.
1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8.
Yeah, some of them must be the.
1, 2,
I think you missed a zero.
1, 2.
I think there's an extra zero. on the
Here?
Yeah.
The very right-hand side should be 4 ones. The
This
first
should be
lead edge
4
is a
ones?
And the next 3 are ones as well.
1, 1, 1. No, but it's the leading edge. 1, 1, 1. I only see 3 ones there.
So it's the bottom of the square of the bit.
Yeah. I only see 3 ones. Okay, well, we'll go with what we got. Yeah, we'll go with what we got. So back to ASCII code. Anybody know what page that on? 24? No, not 24. Okay, 819. So if I have something that's 0, 0, 1, wait a minute, we got to reverse this guy. Oh, bummer. Because most significant bit is transmitted first. Least significant. I still have too many though. Okay, well we're going to reverse it anyway. 1, 1, 1, 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 0, 0. Oh, I ran out of room. Okay. 1, 2, 3, 4, 5, 6, 7. If we do that, 1, 2, 3, 4, 5, 6, 7, and we do that. 1, 2, 3, 4, 5, 6, 7, and we do that. I think we'll be okay. And it just transmitted a couple zeros at the end. Okay, so we're going to go with that. I'm back to my ASCII code. 1, 1, 1, 1, 0, 0. That looks like a T. Right? 0, 1, 1, 0, 1, 1. That looks like a 2. 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1. That looks like a bracket. Perfect.
T2 bracket.
Yeah, it looks like a bracket. Okay, well let's come back to this guy for a moment. Let's turn him off, and we'll come up on him. And all right, so that's what it's saying. It's transmitting. One, 2, 3, 14, 15, 16, 17, 8, 9. Oh, that doesn't help me at all. So that's hexadecimal. Yeah, but what it's transmitting, it's transmitting. So that's the clock pulse. 1, 2, 3, 4. So it's transmitting out of the number that it has. It's transmitting the 4th bit. We'll change that to binary. So 4th bit, 1, 2, 3, 4. That guy, 1, 2. Oh my goodness. 1, 2, 3, 4. Okay, so it's transmitting that guy 0, 0, 0, 0, 0, 1. So it's transmitting 0, 0, 0, 0, 1. But that's not what we saw. What we saw was 1, 1, 1, 0. All right. All right, well, we'll just go with T2 bracket. and say that that's right. Back to 22. Okay. Load section 2-4. All right, so we're here. 2-4, boom. Multisim cannot open this file while it's actively running another guy. Okay, so come there, close this guy. No, we don't want to save anything. 2-4. Read the instructions. This is an illustration of a parallel transmission of 3 ASCII characters, similar to the last guy. Expand the logic analyzer, turn it on, and trace the characters below that are the ASCII characters. The least significant bit is on top. Use ASCII chart to determine the characters. How many clock pulses did it take to do this? Okay, so now we've read the instructions. They're all in English. Okay, so we're going to turn it on. Turn it on. Boom. Okay, thank you very much. And we're going to make it bigger so that we have a chance to look at it. Okay, so it's like that. We're going to go and do a photo capture of this. Okay, did we get it? Yes, we got it. Okay, so we got it, but it's a little big. I'm going to make it just a little smaller. Where is the little smaller spot? There it is. Because we want to see it all. All right, now I'm seeing it all. Okay, so we're transmitting in parallel. There's the internal clock. This is the clock pulse. Okay, so this is the clock pulse going up on top. We have 1, 2, 3 things that are being transmitted. See that? 1, 2, 3. All right. So now we'll look at the first one. The least significant bit is on top. Is that what it said?
Yep.
Yes, it did. So we have a 1. Thank you very much. I can't see that 1. I got a 1. Okay, so I got a 1. I've got a 1. I've got a 0. I got a 0. I have a 1. I've got a 0. I've got a 1. So my ASCII first guy would be 1 0 1 0 0 1 1. Because I have to, this is the least significant bit, that's the most significant bit. Then I look at the second time it happens. I have a 1, I have a 0, I have a 0, I have a 1, I have a 0, I've got a 1, I've got a 1. Okay, I'm going to write it the other way. 1 1 0 1 0 0 1.
How are you getting all of this?
Well, I see the top line, it's high and it's low. See where it's low over here? So it's obviously high there. Now, if it was like this guy here is all one line all the way across, how do I know that that's high or that's low? I know that it's high because when this guy was 0, I'm close to it. Okay, so that's how I know that. All right. My next clock pulse happens over here. I go to 0. This guy is still at 0. He's at 1, 0, 1, 1, 1. So I'm going to write that 1, 1, 1, 0, 1, 0, 0. 1, 1, 1, 0, 1, 0, 0. All right, now I go to my ASCII code table. Now, I'm not going to ask you to do this on a test. I'm not going to ask you to do this as homework because I'm doing it in class, right? So your homework's going to be pretty good. All right, so the first guy, 1010011, looks like an S, capital S. 11001 looks like an I. All right. 1110 100 looks like a T. So obviously the author's trying to tell you to sit down. This isn't that complicated. Okay. Now I go back to the multisim guy for a moment, and I come and open up him, and that does me absolutely no good at all. Even looking at the well, wait a minute, I can look at the ASCII code here, can't I? Well, like I say, it doesn't do me a bit of good to look at what this coding is, because I'm not on the 0th spot. I start over here at the 8th spot. And so looking at the code, I can't come up with what the right answer is. Okay, so the first one we did, total fabrication, I have no clue whether or not that was correct, but perfectly okay. This guy, I'm pretty sure it's SIT. I'm pretty sure that's the case. Next one, E23. E23. All right. I'm on E23. Open 626A. E23. Open 26A. Did we? No, we didn't. Okay. So we got to close this one. File. Close. And we're opening 26A. Okay, that's good. Excellent. Does it say read the instructions? Read the instructions. All right. The normally open relay contacts are used to create a short across the R5 resistor when the clock pulse goes high, similar to figure 2-16. Measure the voltage levels at the clock pulse and at voltage out. Blah, 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 blah. Okay, well, that's fine. I mean, enough reading instructions, right? All right, so this is an oscilloscope. We're going to turn it on. Boom. And we're going to turn it off. Okay, so it's not going to, we can leave it on if we wanted to, but it's just going to keep on doing the same thing over and over again. That's all it's going to do. Okay. So I've got a cursor 1. I'm going to move the cursor 1 to there, and I got a cursor 2. I'm going to move it to here. Okay. I look and I see that channel A is red and channel B is blue. So my channel A is red, my channel B is blue. Okay, so what do I want to know? The open relay contacts used to create a blah, 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 blah. Okay, 1. Measure the voltage level of the clock pulse and voltage 3 with the oscilloscope. Note the relationship between the two waveforms. Okay. Okay, so there it is, all measured. I don't have to write anything down. So that's my A answer. I have measured it. Change the upper resistor to 2K and the lower resistor to 8K. Predict the new voltage levels. Then measure them. Okay, so I'm going to go and we're going to get rid of that. We're going to turn this guy off. So we're going to change the upper one to 2K. Okay, this guy here, I'm going to change him to 2K. Where's the K on this stupid thing anyway? Okay, 2K. Oh, the simulation's running. You have to turn it off to have it make it. In the bottom guy, we're going to change to 8K. Okay, 8. Okay, boom. Cool. All right, so now we're 2K and we are 8K. And now we're going to predict our voltages. Okay, so when what? When this guy is closed, my voltage is going to be 0, just like it was before. Okay, that's fine. But when it's open, what's going to happen? I have 10 volts. I'll have 8 volts. I predict I'm going to have 8 volts at V out. So V out is going to be 8 volts when the clock pulse is high or low. 0. And the clock pulse is 0. So when the clock pulse is 0, this guy's open, I'm going to have 8 volts there. Okay? And when I predict I'm going to have 0 volts when the clock pulse is high. Okay, that's what I'm going to predict. All right, so I come back to here, I turn him on, and I turn him on, boom, and I come back and I look and see what I've got. The clock pulse is the same, but the channel B is now 8 volts. See the 8 volts right there? Yeah, it says 8 volts on it. Did I get it? I did. All right, so my prediction is true. I'm expecting 8 volts, and I see 8 volts. All right?
What was A? 0 volt?
What was A?
Yeah.
What did they ask me? What was A? This just told me to measure it, right?
Oh, is that all it was?
Yeah, it just told me to measure it.
Oh, I thought.
Where is it? So that's my prediction right here. It was 5 volts. So in the A part, I had 5 volts in channel B, V out, when voltage was low, and I had 0, basically 0. It says 2 microvolts. Well, 2 microvolts is 0. You can't see that. Okay, that's, where's my eraser? Boom. Okay, so you have 5 volts, and you have that guy, 2 microvolts, which is essentially 0. Okay, so that's what I had there. Now C, if the normally closed relay contacts were used, what would you expect the waveform to be? If the normally closed relay contact were used. Okay, so normally closed is not connected. Right, so we're going to use it. All right, so I'm going to predict it will, instead of being an inverter, it was an inverter the first time, right? I'm going to predict, that's the wrong thing to do. I want to be on, what do I want to be? Okay, so this is B. All right, so this is C. I'm going to predict. I have a buffer. So before I had an inverter, when I was high as low, and when I was low as high, I'm going to predict if I use the other guy, I'm going to get a buffer. It's off. I'm going to disconnect this wire, and I'm going to connect the normally closed guy. Just like that. Then I turn this guy on, and then I'm going to hit the button. Boom. Now I've got a buffer. buffer was correct. Okay, thank you very much, gentlemen. We'll